Hello, everyone. My name is Beijing from Nanyang Technological University. Thank you very much for having me. So today I want to talk about fair division with mixed divisible and indivisible goods. So this is a joint work with Zihao Li, Jinyan Liu, Shengxin Liu, and Xinhang Lu. So the topic of the talk today is fair division. So it deals with how to fairly divide some resources. This is part of the theory that has been around since the 1940s. It's a theory that has been studied by economists, mathematicians, and also political scientists. So I want to start by giving you a very simple motivating example about fairly allocating resources. So assume that in heritage division, there are multiple heirs, and together they may want to divide some resources. It could be a piece of land or other things such as some valuable artworks, and they want to do it in a fair manner. So I list here the land and artworks, these two specific examples on purpose because they represent two major classes of fair division. And they are characterized by the type of resources to be allocated. The first class is divisible resource allocation. Here, land can be divided into arbitrary precision, so it's a divisible resource. And the second class, which has also gained quite a lot of popularity over the past few years, is indivisible resource allocation. Here we are to allocate indivisible items such as artworks here or others like cars or houses. In this talk, I will discuss each class very briefly separately, and then I will discuss how to combine these two settings altogether. So we want to start from the divisible resource allocation. And there are many different models in this setting. I want to focus on a very simple, classic, and abstract model known as the cake cutting. So in the cake cutting problem, we want to divide a single heterogeneous good, which was also called a cake, among a different set of n agents. So we're going to represent this cake mathematically as an interval between 0 and 1. But the idea is, first, this resource is one-dimensional, and second, because this is heterogeneous, that means different parts of the cake may have different values to different agents. We have a set of agents who want to divide this cake, and we say a piece of cake is just a finite union of these joint intervals. The idea here is that it does not have to be connected. It could be the union of many different intervals. In the end, we want to find an allocation, which is essentially a partition of the whole cake into n different pieces. So AI is the piece of cake given to agent I. And we require that these n pieces are mutually disjoint and their union should be the whole cake. We're also going to assume that every agent has a valuation function that maps each piece of cake to a real value that measures how much this agent has value for this piece of cake. We're going to assume that this function could be very general. It satisfies only the following very general conditions. First, we're going to assume it's additive. That means the value of an agent on two pieces of the cake will be the sum of this agent's values for each of the pieces. We're going to also assume normalization, that is, every agent value the whole cake as unit value. And finally, we're going to assume that this function is divisible. That means for every piece that values alpha to some agent, and for any lambda that is between 0 and 1, we can always find a smaller piece that values exactly lambda times alpha for this agent. So these are all the assumptions that we have for this valuation function. In some other words, you can also intuitively assume that this valuation function is a probabilistic density function. Also, because in the most general case, a valuation function may need infinitely many bits to be fully represented. So in order to cast this problem as a computer science problem, we're going to need to deal with the size of the input. And here it's more useful to consider the query complexity. In this case, the most widely accepted query complexity model in cake cutting is called the Robson-Webb model. In this model, we're going to assume that we don't have full information of the valuation function. Rather, we only have two types of operations that we can query to the evaluation of each agent. These two valuation functions are, first is evaluation of any agent on any interval of the cake. They're going to return this agent's value for this interval of the cake. And the second is a cut operation. That is, you give a starting point, you also give another value, you're going to return the end point such that this piece, this interval, going to exactly value this value alpha to this agent. All right, so this is the basic model. Now let's see some examples of what are some of the fair protocols. What are some of the fair protocols look like? We're going to start with two players, and I'm going to give you a very simple example of a fair protocol for two players. So this protocol is called cut and choose, and I believe most of you may have heard or used this protocol before. It's very simple. Assuming that we have two players, two agents, who together want to allocate a single cake. So the idea is this protocol will first ask the first player, let's say the red player, to cut the cake into two equal halves according to her own valuation. And then we're going to let the second player, the blue player, to look at these two halves and pick his favorite half. Okay? So in this example, the blue player thinks the second half values 3/3, so he's going to pick the second half, and then the red player, the first player, is left with the first half. This is a very simple protocol for two players for dividing a cake, but it is also a fair protocol. So what type of fairness conditions that this protocol can satisfy? Now we talk about fairness properties. In this talk, we're going to talk about mainly two fairness properties. The first one is called proportionality. We say an allocation is proportional or satisfies proportionality if for every agent, the piece that is assigned to that agent will be valued at least 1/n for that particular agent. Okay? If this allocation satisfies this property, we say this allocation is proportional. The second fairness property is known as envy-freeness. This is also very interesting. It says that an allocation satisfies envy-freeness, or an allocation is envy-free if and only if for any two agents, I and J, it always satisfies that agent I will think that in agent I's own eyes, he will think the value of his own piece is at least as much as the value for agent I of any other pieces. So this is the second condition. And if you look at these two fairness conditions, it's not really hard to realize that in this case, envy-freeness is a stronger fairness notion, in the sense that envy-freeness always implies proportionality. If allocation is envy-free, then it is also proportional, but the reverse may not be true. In addition, envy-free allocation also enjoys the following nice property, is that it always exists in a very general scenario for any number of players, and also can be found in bounded time in the Robinson-Webb model. The last result is actually not an easy result. It has been a breakthrough. It was found by Harrison Aziz and Kevin McKenzie in 2016. So this is the model for divisible resource allocation. Next part, we turn our focus to the indivisible resource allocation. So here, the idea is the resource to be allocated may consist of indivisible items like cars, jewelries, or some artworks. The model here is actually quite similar to that of the divisible resource allocation setting. So here we want to allocate a set of indivisible goods, a set of m indivisible goods among a set of n players. Now we say each player gonna receive a bundle of items, which is a subset of these M indivisible goods. We again require that in the allocation, different bundles should be mutually disjoint, and their union should be the whole set of goods. We're also going to assume that each player will have a validation function, and now we're going to assume they have an additive validation function. That means each agent will have a value for each of the item, and this agent's value for a bundle of items is just going to be the sum of this agent's value for each of the items. Now we talk about fairness. So for fairness, although seems like NV-freeness is still a valid option, but we cannot use NV-freeness anymore because with indivisible resources, and NV-free allocation may not always exist. So what we want to think about here is that what kind of NV-free allocation notation can we always guarantee in the face of indivisibility? And the notion we will use here, which is also very well studied in the indivisible setting, is called NV-freeness up to one good, or short for EF1. The meaning is that we say an allocation satisfies EF1 if any NV that an agent has towards another agent, if it exists, it can be eliminated by removing some good from the later agent's bundle. We can put this into mathematical formula. It says that for any I and j, either agent I doesn't envy agent j, or if agent I envies agent j, there must exist some good in agent j's bundle, such that after removing this good, agent I now thinks his own bundle values at least as much as agent j's bundle. NV-freeness up to one good also enjoys a couple of nice properties. It always exists for any number of players. Also, it can be found in polynomial time by a number of different algorithms. All right, so far we have talked about two different models, divisible resource allocation and indivisible resource allocation. We talked about what are the fairness conditions, the fairness notions that we want to use in different models. In particular, we focus on NV-freeness for divisible and EF1 for indivisible. Now we come to an interesting question is, what if we have both divisible and indivisible items at the same time? This actually happens a lot in practice in real world. For example, in heritage division, sometimes the heirs may want to together allocate a piece of land together with some set of artworks or some other cars or houses. I can give you another example in this event of a pandemic. Okay, sometimes we may need to allocate some scarce medical resources among different patients. And here, the medical resources may also contain some divisible goods, such as money, the time spent on a ventilator, for example, and as well as some indivisible resources, such as masks or some other personal protection equipments. So our question we want to study in this talk is that, how do we define fairness when we have both divisible and indivisible goods presented? Okay, so to talk about this mixed goods setting, we need to also formalize the model. So we say in the mixed good model, now we want to divide a set of M indivisible goods and one divisible good, which is a cake. So here, the most general case is we may have a set of many cakes, but without loss of generality, we can combine all the cakes together into a large, big cake. So this assumption is without loss of generality. We're going to assume that every agent now has first a validation function for the indivisible goods, and then it also has a density function, another validation function for the cake. Now an allocation is just consists of, again, n parts, where AI, the resources that we want to give to agent I, consist of first a bundle of indivisible items, mi, and also a piece of cake, ci. Finally, we'll again assume additive validation, that is, the valuation of agent I for this allocation AI is just going to be the sum of his value for the bundle of indivisible goods plus the value for the cake. So this is the model. Now we ask, now we look at fairness. So we'll ask ourselves what kind of fairness notions that we want to use in this mixed goods setting. So we ask ourselves, what do we want in a good fairness definition? Well, I argue there are two things that I really care. First, we should guarantee that this fairness notion should always exist in this domain. And second, it should reflect what we normally perceive as fair in a very intuitive way. So let's look at some candidates. First, it's not really hard to see that unfairness or EF1, unfairness up to one good, may not be a very good candidate in this mixed domain. Why? Because unfairness may not always exist if we only have indivisible resources, and unfairness up to one good doesn't always give us a fair solution, for example, if we only have one cake. Okay. And the next idea is that how about we use unfairness, we use an unfair allocation for the divisible goods, and then we use a EF1 allocation for the indivisible goods, and finally we combine these two allocations together. So next, I want to argue via a simple example that this is also not a good option. So let's assume the following very simple example. Assuming that we have two players, and together they want to allocate a house in which both player values at $2, together with $10. So here the money can be considered as a divisible good. So in this setting, let's see what happens if we apply this EF for divisible good and EF1 for indivisible goods solution. So first, we want to allocate the house. Because we only have one indivisible good, we can give it to any of the players. Assuming that we are giving it to the first blue player. Next, we want to allocate the money, the $10 among the two players. And if we want to find an EF allocation, the only solution is we want to give each player $5. So now if you look at this allocation, you can see that intuitively, this doesn't look very fair, right? This is because the second player gets $5, but he doesn't get the individual item, the house. So intuitively, he should be able to get more money to compensate this house. Okay? So in this case, I would argue that a fair allocation should be that you want to give the first player a house and $4, and you want to give us the second player $6 to compensate this house, which is worth $2. So I hope that through this very simple example, I can convince you that it's not a really easy question to define fairness notion for mixed goods setting. Basically, it's not always a good idea to simply apply unfairness for divisible goods and EF1 for indivisible goods and simply combining them together. What we really need is a new fairness notion for mixed goods setting in a very natural and very non-trivial way. So now we come to our setting. So the main results in this talk is that in this work, we propose a new unfairness notion for mixed goods setting, which we denote as EFN. What does this notion mean? We say an allocation in the mixed goods setting satisfies unfairness for mixed goods or satisfies EFM if the following condition happens. So we say for any two agents I and J, if agent J's bundle consists of only indivisible goods, okay, then agent I gonna evaluate its own bundle with regard to agent J's bundle using the EFY criteria. In other words, we require that there should exist some item in J's bundle such that after removing it, agent I now prefers its own bundle to agent J's bundle. But otherwise, that means if agent J's bundle consists of any amount of divisible goods, okay, we're going to apply now the more strict envy-free condition. Okay, so we're going to require that agent I should value his own bundle at least as much as his value for agent J's bundle. Okay. So let me say it again. This is a very important notion. We're going to require that agent I use EF1 to value his bundle towards agent J's bundle only if agent J's bundle consists of only indivisible goods. If agent J's bundle has any amount of divisible cake, then the other players gonna evaluate their own bundles to agent J's bundle using the EF condition. If this condition is satisfied, we say this allocation satisfies EFM. It's not hard to see that this EFM fairness notion is a direct generalization of both envy-freeness and envy-freeness up to one good in the divisible and indivisible setting. So in the sense that when we only have divisible goods, this EFM notion reduces to envy-freeness. When we only have indivisible goods, this EFM reduces to EF1. Okay, so now I hope I convinced you that this is indeed a better solution in the mixed good setting. But next question, of course, the next big question is, does an EFM allocation always exist in any mixed goods domain? So our main result we're going to present in this talk is that we showed an EFM allocation always exists in the mixed goods domain for any number of agents, and also it can be found in polynomial time, but with some caveats. So the rest of the talk, I want to give you a favor of the proof of this theorem. So I want to show you a proof sketch. The idea is very simple. We want to prove this theorem using a constructive argument. That means we will provide a constructive algorithm that can produce a EFM allocation. This algorithm will start with an EF1 allocation of all the indivisible goods. And then it will iteratively and very carefully add more and more cake to some of the agents in this allocation. And the idea is we want to maintain that the EFM condition is satisfied throughout the process. And in the end, when we allocate the whole cake, we have found an EFM allocation of all the resources. Okay, now let's look at some details of this proof. To show this proof, we're also going to need some additional notions. So we're going to define a following notion called the NV graph. An NV graph is a directed graph among agents. That means for given any allocation, we can construct an NV graph of the agents. This graph has two types of edges. The first type is called an NV edge. That is, we're going to construct an edge, NV edge from agent I to agent J if agent I thinks that his own bundle values less than agent J's bundle, if this condition is held. If this is the case, we're going to have an NV edge from I to J. The second type of edges is called equality edge. In this case, we say if agent I thinks his own bundle has exactly the same value as agent J's bundle, then we're going to have an equality edge from agent I to agent J. So we're going to use a very simple example to demonstrate. This is an example of three agents together dividing three indivisible items. These numbers are the valuations of these agents to each of the items. So we look at a particular allocation that assigns the house to the first agent, the car to the second agent, and the diamond to the last agent. So based on this allocation, we can construct the following NV graph of these three agents. So you can see that the blue agent has the house. He thinks in his own eyes, the house has the same value as the car. So that means there is an equality edge from the blue player to the orange player. Similarly, the orange player has an equality edge to the blue player. But the orange player also has an envy edge to the green player, because in the orange player's eyes, the diamond, which is valued 4, is valued more than the car, which is valued 3. So this is the envy graph of this particular allocation. All right, so this is envy graph. Next, we also want to, based on this envy graph, we also want to introduce another notion which we call an edible set. So it defines as following. Given an envy graph, we say a subset of agents is called an edible set if it satisfies the following conditions. So first, there should be no envy edges within this set S. So within this set of S of agents, there cannot be any strict envies. And second, we require that there is no envy edge nor equality edge from anyone outside S towards this set S. If a set of agents satisfy this condition, these two conditions, we call this a subset of agents an edible set. Again, in this example, the same envy graph, it's easy to check that the bottom two agents, the blue agent and the orange agent, together they form edible set. Okay, so this is the definition of edible set. So intuitively, what an edible set means is that for any agent outside of this set, such as the green player here, this agent would think that its own bundle has value strictly more than any of the bundles of the agents within the edible set. So with this intuition, we can basically say that when we have an edible set, the solution is we should be able to add some amount of cake to the agents in the edible set while maintaining this EFM condition. So the idea is how much cake and in what fashion should we add to the agents in the edible set? Here, we're going to say we want to add the cakes to the agents in this set via a perfect allocation. So perfect allocation in cake cutting is an allocation such that every agent would think that all the pieces will have exactly the same value. So it was proven by Long in 1987 that in any cake cutting scenario, for any number of players, a perfect allocation also always exists. So in this scenario, we want to add some part of the cake using a perfect allocation to the agents in this edible set. And we want to add only a very small amount until some agents outside think there's a new equality edge from anywhere outside to inside. So this is what we want to do in this condition of in the presence of an edible set. The next notion is also defined based on an envy graph. We say an envy cycle in an envy graph is a cycle, a directed cycle in this graph with at least one envy edge. The other edges could be equality edges, or it could also be envy edges. But together, this would form a directed cycle. Again, in this same example, you can see the darkened edges together they form an envy cycle. So if in this envy graph we have an envy cycle, then what should we do? It's also very simple. Here, the solution is we can apply a procedure called envy cycle elimination. That means in the envy cycle, every agent in this cycle would think that the bundle of the next agent values has more value. So we can assign each agent in the cycle the bundle that it points to. So using this, after this reassignment, every agent gets a weekly better bundle for himself. And also at least one envy edge is removed. So this is, again, we are not introducing any new envy, and we removed at least one envy edge. This is what we do in the when we have an envy cycle. All right. Finally, now we have defined two different structures, an edible set and an envy cycle. We have also discussed what do we need to do when we have each of the structure. The final part of the proof is a key lemma that connects these two structures together. So finally, we show that in any graph at any point of time, there always exists either an edible set or an envy cycle. So we could always see at least one of these two structures in this graph. But the idea is now becomes very simple. That means at any point of time, we look at whether we have an edible set or an envy cycle, and then we're going to apply the corresponding procedure. So this would allow us to always make progress. We're going to repeat this process until all the resources are allocated. And we can also show that the process will eventually terminate. The allocation is also always EFM. So in the end, we have found an EFM allocation for this set of mixed goods. And that's the end of the proof. All right, so now we have shown the existence of an EFM allocation via a constructive algorithm. But as I said, it has a caveat. We say this is a polynomial time algorithm, but only if we know how to find perfect allocations in K time. But very unfortunately, although we know that a perfect allocation always exists, we have a very strong impossibility result saying that perfect allocation cannot be implemented in the Robson-Webb model in bounded time. So this leaves us a very interesting open question, is that does there exist a bounded EFM particle in this Robson-Webb model? And I believe this is one of the biggest open question in this domain. Finally, we spend a little bit of time to talk about approximations. So since we don't know how to find a bounded EFM particle in the Robson-Webb model, instead we say, what can we do, okay, in the Robson-Webb model? And it turns out that we can find an approximate version of this EFM allocation quite efficiently. So here we define an epsilon envy-free for mixed goods fairness notion. This notion is exactly, almost exactly the same as the EFM notion, except that in the second case, okay, when AJTCS bundle has any amount of divisible goods, we can have an approximation, an error of epsilon on this side. So this is an approximated version. And we have also a theorem saying that if we only ask for an epsilon EFM allocation, then in the Robson-Webb model, we can indeed find an epsilon EFM allocation in time that is polynomial in the number of players, in the number of indivisible items, and 1 over epsilon. I also want to mention that this is not a trivial algorithm because we cannot simply replace the previous perfect allocation oracle by an epsilon perfect allocation oracle, because that would require exponential running time. But here we want to find a polynomial running time algorithm. So we need to introduce some new techniques. We will skip the details here. So finally, I want to summarize. In this talk, I discussed how to find, we discussed fair division in the presence of a mixed type of good. So this is a unified setting in fair division. It generalizes both divisible and indivisible setting. Our main contribution is we propose a new fairness notion for this mixed good setting, which we call EFM. Intuitively, it captures what fairness should mean in this domain. we also showed that it always exists for any number of players. It can also be found in polynomial time efficiently, albeit with some caveats. There are some interesting open questions. For example, we can ask, can we combine EFM with some efficiency considerations such as Pareto optimality together? Or we could also consider, how do we define fairness when we have both goods and chores? And can we find it? Can we show its existence? So in general, I believe this is a very new research direction for this mixed good setting, and there are lots of new questions to think about. And with that, I end my talk. Thank you very much.
And thank you, Xiaohui, for the nice talk. So I've collected a few questions from the audience. So the first question is, for divisible items, we can cut them into pieces and then treat them as indivisible goods. So then we can consider the EF1 allocation for those goods, for all the goods. So how does this allocation compare to your EFM allocations? Sorry, you're muted.
All right. Yeah, thank you. I think this is a very interesting question. It is indeed possible for the agents to, I need to think about this. I think it's possible that this is a valid approach for each agent to cut the pieces to cut the cake into small epsilon pieces. This is going to create a large number of cuts to the cake, and then we view each small part as an indivisible item, and we do the EFM allocation. I believe that in the end, if we do the allocation this way, we can indeed, this is indeed an approximation version of the EFM. That is, this is an epsilon EFM allocation. The problem is that since now we have many small pieces, to find a EF1 allocation among these many pieces is not a very easy task.
Okay, I see. So this is different from your algorithm for finding epsilon.
Yeah, it's different. We're not using this algorithm.
Okay, thanks. So the second question is, are the EFM allocations unique in the non-trivial scenarios?
Yeah, another very good question. EFM allocation is not unique. A simple example is we know when there are only indivisible items, so EF1 allocations are not unique. And for k-cutting, EF allocations are also not unique. So combining them together, we do not have uniqueness.
Okay, great. Okay, so I guess that's the end of this talk. Let's thank Xiaohui again.
Okay, thank you very much.
So our next talk will start from 7. So see you soon.